The final topic that we want to look at is the idea that when you have current moving in a wire, it produces a magnetic field around that wire. And if you stick another current carrying wire somewhere within that magnetic field, the end result is it's going to feel a force from the magnetic field produced by the first wire. So that's what this picture is trying to illustrate here. Again, with the challenge of three-dimensional phenomena and a two-dimensional representation. But you have current flowing in the wire in this direction in wire A. If you use your field right-hand rule, so if you orient your thumb in the direction of that current flow, your fingers are going to curl in the direction of the magnetic field. And so the magnetic field is going to go around that wire over here on the right-hand side where wire B happens to be located. That magnetic field would be going in the downward direction. Then you switch gears and you go to the first right-hand rule we learned, the one with the force vector, the current vector, the magnetic field vector, and the force vector, your three fingers. So if you orient your index finger of your right hand in the direction of current flow in wire B, you get that, and then you curl the fingers down into the direction of the magnetic field due to wire A. Your thumb will be left pointing back towards wire A, which is the direction of the force on wire B due to wire A. You could do that same logic, right? B is making a magnetic field over here at wire A. So we could draw the magnetic field due to wire B over here. And then if we oriented fingers in the direction of the current flow in A, curled them in the direction of the, whoops, I screwed that up, didn't I? This one is not downward. This one is upward. All right. Yeah, because here's my current flow, and then my fingers are curling sort of out of the page there. So the magnetic field is up here, and if you put your fingers, then the index finger in the direction of the current flow in wire A, curl that in the direction of the magnetic field due to wire B, you are left with a force vector that is back towards wire B. That would be the force that wire A puts on, or rather wire A feels from wire B. And these are going to be Newton's third law of force pairs. They follow that same rule we're carrying over from physics 1, equal opposite directions. Now, what would change if we changed the direction of current flow in one of these wires? Let's just say B is going the opposite direction. Well, the magnetic field due to wire A is in the same direction, but if current flow is reversed, that reverses the force as well. And so there's a couple of conclusions you can make from this. If the two wires are carrying current in the same direction, then the forces they put on each other are attractive. And if they are carrying current in the opposite direction, they are repulsive. And some problems ask you to work out various details of that. This is just a ranking task that takes advantage of that opposite and same direction current flow in wires to ask you about what the magnitude of the net force on the central wire is due to the currents in the other wires, with the greatest first in this particular ranking. So I'm going to walk through, well, I'm going to do them all, but I would encourage you to perhaps, if it makes sense to you right now, pause the video and see what your ranking is, or watch me work through A and then pause the video and do B, C, and D. So I'm just worried about the center wire in this arrangement. I'm going to number my wires, so that's going to be 1, 2, 3, 4, and 5. And what would wire 3 feel in terms of forces on that? Well, wire 3 would feel a force from wire 1. 1 and 3 are current flow in the same direction. So I'm going to have a force from wire 1 that is toward wire 1 on wire 3. 2 is carrying current in the opposite direction to wire 3, so that's going to cause a repulsive force. That's going to push wire 3 away, and because 2 is half the distance away from 3, the force is twice the size. So there's the force from wire 2. If I look at wire 4 is carrying current in the opposite direction to wire 3, so it's going to push wire 3 away. There is also a force in that direction, so there is the force from wire 4. Number 5 is going to be an attractive force, so pulling wire 3 towards it, but it's twice as far away. So that is something like that. And the net result out of all of that is that the net force on the center wire in this particular arrangement is 0. Well, let's work it out for our other 3 sets here. Again, I'm just going to always assume 1, 2, 3, 4, 5 across there. So if current's going into the page, this one is going out of the page. 1 is going to produce a repulsive force on that. So there's the force from wire 1. 2 is similarly going to be a repulsive force, and it is twice as big because it's half the distance away. Let's see, 4. 3 is current going into the page. 4 is current going into the page. So I have another situation where that is attractive. The force from number 4. Number 5. All of these forces in this particular arrangement are in the same direction. So can't even fit it scale-wise on here, but the net force is a big force in that direction. Let us see. Okay. Arrangement C. Here's current coming out of the page. Out of the page, out of the page. So that's giving us an attractive force from wire 1, a repulsive force from wire 2, a attractive force from wire 4, and a repulsive force from wire 5. But these don't all completely cancel because of the relative magnitudes of things. So I'm going to have a net force in this direction that is about that big. And the last situation, so separate these out a bit. Current going into the page in the center wire. Here, out of the page, or sorry, into the page, same direction of current flow, so that's an attractive force. So 1 pulls 3 towards itself. 2 is repulsive. 4 is attractive, but that's to the right as well, and that's again a bigger force. And 5 is also attractive because that's current into the page, so that is carrying, it's producing rather a force to the right that's about that big. So 5 and 1 are going to cancel, but 2 and 4 together are going to add, and that's going to give me a net force something like this, which means my ranking, I believe, here's my biggest one, right? I can't even fit that to scale on the page. So the net force in scenario B is greater than, here's my next one, the net force in scenario D followed by net force in scenario C, and finally the net force in scenario A, which was 0.